Hi everybody, welcome to this lecture which essentially covers the third chapter in P&G. And we're basically looking at working with an application that was built at the University of Texas for the purposes of testing various equations. And using this software, which is called ProofPad, you can actually thoroughly test software to make sure that states are maintained in a way that makes the overall function of a component predictable. And of course, in most contexts, you have to build with the possibility for failure. However, using software such as ProofPad, software developers and engineers and scientists, mathematicians can utilize ProofPad to get a feel for whether or not a particular way of thinking about natural numbers makes sense. And so we essentially, in most of the work we're doing, we're limiting ourselves to the natural numbers, which are all the integers greater than or equal to 0. And then in some contexts, 0 is eliminated, and we can still find places in which integers greater than or equal to 1 are also called natural numbers as well. However, in I think a couple places in the reading, you'll find discussion of the need to eliminate 0. Think, for example, if we're creating a variable which is going to be used as the divisor in a ceiling or floor operation, or potentially just a plain old modulus. We don't want there to be a 0 in the denominator. So if we're testing, an algorithm out using ProofPad, we have to take into account the fact that 0 is not going to be wanted if the variable that we're talking about occurs as the divisor in modulus, floor, or ceiling. And we also look at prefix notation, which you'll find in some contexts is described as reverse Polish notation, or RPN. And some scientific calculators have a mode to enter arithmetic expressions using prefix notation. And I'm confident that most of you guys will be comfortable with prefix notation. In some ways, it simplifies things. It is different from the notation we're most familiar with, which is infix notation, in which we have two operands and an operator right in the middle, and that's the notation we're most familiar with. However, it also makes sense, in the field of computer science to learn about prefix notation as well, because in computer languages, such as Lisp and its various dialects like Scheme, you'll find that prefix notation is actually utilized. So having knowledge of prefix notation can really work to your advantage as a technologist. So ProofPad and ACL2. ACL2 is short for computational logic for applicative common Lisp. And the software we are utilizing is called ProofPad, which is available at proofpad.org. And ProofPad is a tool that provides a convenient way to write, test, and reason about programs written in the ACL2 dialect of a computer programming language called Lisp. And Lisp is actually pretty straightforward. The, data structure that's used in Lisp is typically a list. And that's like a sequence of integers. It could be a sequence of strings. And I think there's also the possibility of having sequences of floating point values as well. And the Lisp is commonly referred to as a functional language in which, there's kind of a heavy reliance upon recursion. And this is something that is probably somewhat new to some of you. However, I think you'll find, if you pursue studies further in computer science, you'll eventually encounter Lisp. And ACL2 works kind of, from a syntax standpoint, works the same way as Lisp does. However, ACL2 is a subset of Lisp, which means, if you want the full functionality of Lisp, you actually have to install it. And it is available. There are open source packages available for multiple platforms. And I think once you download and install ProofPad, you'll get a feel for the way Lisp works. And if you have the time, there's no reason why you shouldn't consider experimenting writing code in Lisp. So ACL2 includes a mechanized logic that supports rigorous checking of the reasoning process. ProofPad can be installed in Windows, OS X, and various flavors of Linux. And I recommend taking a look at the Wikipedia entry on ACL2. It's right here. And also take a look at the official ACL2 website. This is University of Texas at Austin, which is an excellent institution. And here's a screenshot of what ACL2 looks like in Mac OS X Sierra. That's the operating system I'm running. You can see the prefix notation. Notice the operators come first. And over here at the left, down the left-hand column here, we have these green boxes which indicate, that there isn't a problem with the code on that line. And you can see these green boxes next to these check expects. And these calls to check expect are just testing out addition. So you can see over here, 2 plus 2 is equal to 4. So this call to check expect returns true, which is represented by this green box over at the left. And you can see this last check expect doesn't pass. So it has this red box with a black X through it. And, this is very simple use of ProofPad. And I think these are actually some of the examples that are covered in the Chapter 3 reading in P&G. So while you're doing the reading, or perhaps upon a second read of Chapter 3, you might consider working through some of the examples to get a feel for how ACL2 works. And one of the things you'll notice is that there are a lot of parentheses. And that is something that makes working with ACL2 somewhat complicated, because you have to be very careful with the parentheses. The parenthesis defines scope. And scope is basically the context in which a variable or a function is visible. And that's very important when you're writing these check expects. You can see this last one has, 3 right parentheses. And those match off against parenthesis over here at the left, and then a little bit along towards the right. So you have to be certain when you're working with ACL2 to pay particular attention to where you place parentheses, and you can count them off as well. That's what I actually like to do to see if there's a problem with parenthesis matching. So if you start at the beginning at this first line of code, you can see there's 1 open parenthesis. So you can add 1 to the open parenthesis count. And then you can see we encounter a close parenthesis right over here at the right. So that reduces the open parenthesis count by 1, and the result is 0. And that means, in this first line of code, that the parentheses match. And that's what we want. So we looked at the screenshot on the previous slide. As I mentioned, I'm running OS X Sierra. And if you install ProofPad in either Windows or Linux, the interface may appear slightly different. And notice that we write ACL2 code in the large rectangular box up top. And then, as we discussed previously, the column down the left side of the interface indicates tests that pass with a green box and tests that do not pass with a red box containing an X. So we are, familiar with arithmetic expressions written utilizing infix notation. Here you can see we have 2 plus 2 equals 4. We have 7 times 16 equals 112. And these expressions written utilizing prefix notation appear as follows. You can see the operator comes first, followed by the two operands, and the result is the same, 4. And this is just 2 plus 2 is equal to 4. And here you can see the product, 7 times 16, written in prefix form, in which the multiplication operator comes first, followed by the two operands, and you can see the result is the same, 112. And there is a test in the reading for the associative nature of the addition operator, and this test of the associative equation of numeric algebra was introduced on page 16 of P&G. I believe that's in either chapter 1 or 2. And examine the code we can write in ProofPad to test this equation. So we have a code that you could just copy and paste this directly into ACL2. You can see we're loading resources, and then we're defining a property which we're calling associative test, and we're generating 3 random integers, x, y, and z. And then down here towards the bottom of the code, you'll find we have our test, and we're just testing to see that x plus y plus z is the same as x plus y plus z. And the parentheses kind of give it away, the fact that we're testing for the associative property of addition. Notice how we group these variables differently. So in this first part of the test, we're creating the product y plus z plus x. And in the second argument to the test for equality, we're first adding x to y, then we're adding that to z. And if this test passes, what we have the assurance of is that the associative property of addition that's defined on page 16 of P&G is correct. That is true. And that's kind of the goal that we're seeking with ProofPad. It's to be able to write various equations that we can use to confirm whether part of an algorithm, or even perhaps an algorithm in its entirety, is going to produce the results that we seek. And that's the main purpose of ProofPad for computer scientists. And here's the associative test that I entered in to ProofPad, and you could do this too. You could try this out too. Notice all the tests pass. So you can see down the left-hand column here, we have a big green box, and that means that specifically these last two lines of code pass, and that's really what we're most concerned about. Because that's the associative nature of addition, and we can test the associative nature of addition using ProofPad. And also, again, I just want to reemphasize that we're using prefix notation, which means the operator comes first, and that's something I think think you'll become more familiar with the more you utilize prefix notation. So if you're writing code in Lisp, or you're writing code in a subset of Lisp, which is the software package we're working with, ACL2, you'll find you'll eventually become more familiar with the way prefix notation works, and that's a good thing because it's used in a wide variety of contexts, not just in computer science, but also other disciplines as well. Mathematics, you may find use of prefix notation in the sciences, other sciences as well, and take some time to test these chunks of code out in ACL2, because I think it'll give you a better feel for the way things work, and also you'll eventually confront the difficulty surrounding parenthesis, and you'll find that same operation, parenthesis matching, in other computer languages as well, Java included, Python, and that's something that also applies in some computer languages to other sorts of tokens. For example, in Java, we have the curly braces, and those also have to be matched. And here's just an example of working with lists. As I mentioned, Lisp, which is the language that provides a platform for ACL2. The list is kind of like the most fundamental data structure. And here you can see what we're doing is we're writing these check expects to see if the append operator works the way we would expect it to. So for example, if we append the list 1, 2, 3 to the list 4, 5, we expect the resulting list to be 1, 2, 3, 4, 5. And you can work through these other examples as well to see that the tests should evaluate to true. And it is also recommended, not just to inspect this code, but also to try it out, to kind of get behind the wheel and get a feel for how ACL2 works. And this is a test written in ACL2. It's the additive law of concatenation test. And you can see we're generating a random list of random integers. We're generating a random list of random integers, which is represented by XS. And then also a second random list of random integers, which we're assigning to this variable ys. And then we're simply checking the length of these two lists appended together. And we're comparing that to the sum of the lengths of each of the lists. And so we would expect that if append is properly functioning, that this test would evaluate to true. And so we can use ACL2 to get a feel for whether or not the concatenation operator, or rather the length operator, accurately reflects the concatenation of these two randomly generated lists of random integers, one called XS and the other called YS. And so I just also wanted to briefly recap or provide a refresher on natural numbers. A natural number is an integer that's 0 or more, and some treatments start the naturals with 1 rather than 0. However, in the computing domain, starting with 0 simplifies formulas. And here you can see we're checking modulus, which is the remainder after long division. 2 goes into 12 6 times with a remainder of 0. So we would expect this first check expect evaluates to true. And take a moment to work through the other examples as well to make sure the result of the modulus call to modulus is accurately reflected in this second operand of the check expect. So if the modulus is not equal to this second argument, then the check expect would most likely evaluate to false, in which case you'd see that red box with the black X through it over in the column at the left in ACL2 or proof pad. So you can also, if you just eyeball these, you can see that these tests, each of these tests, should evaluate to true, and by all means play around with it. Try to test out check expects that should evaluate to false. And either way, it basically confirms whether or not a particular approach to implementing things is going to lead to successful implementation. And there are many points in the development of algorithms when it makes sense to use software like ProofPad to get a feel for whether or not what one plans on implementing is likely to be successful. We also explore modular arithmetic, which is also called clock arithmetic, and this produces integers in a fixed range, 0 through m minus 1, where m is greater than 0. And m is a natural number which we can call the modulus. And if x is an integer, the formula x mod m denotes the remainder in the division of x by m. And so what we have here is the opportunity to write some tests in ProofPad to prove whether or not this statement that the modulus is always going to be greater than or equal to 0 and less than m holds water. And we can use ProofPad to test modular arithmetic. So modular addition, subtraction, and multiplication are consistent with ordinary arithmetic. And here you can see that these expressions on the left are equivalent to these expressions on the right. And this basically follows the sort of mathematics that one might encounter in a course on algebra. So you find that the mod operator can be applied to both x and y prior to calculating the final mod. And so notice that these first two calls to mod are this part of the expression is calculated first, and then after we sum the mod of x by m and of y by m, we then calculate the mod of this first part of the equation by m. And you can see that this expression on the right is equivalent to this expression on the left. And that also holds true for subtraction and multiplication. And so you can see that in some cases this can simplify expressions one might encounter in the development of algorithms. And fortunately, ACL2 supports modulus. However, when you're writing modulus in ProofPad, it is prefix notation. So notice in ACL2, the operator comes first, which is mod, which is then followed by two operands, x and m. And so mod xm delivers the remainder of x divided by m. Here's an interesting bit of code that you could potentially test out in ProofPad. This code here indicates that the remainder does not change when the divisor is added to the dividend. And when you think about this, it kind of makes sense. It's just the nature of modulus. So we define a property called mod invariant. We do that by writing this keyword def property followed by this name for the test, which we've chosen as mod invariant. And then we're declaring a variable called divisor minus 1, and we're assigning a random natural number to divisor minus 1. And then we're also declaring a second variable called dividend, and we're assigning a random natural number to dividend as well. And then we're using this let expression, which enables us to then substitute in value for this variable divisor. And divisor is going to be divisor minus 1 plus 1. Divisor minus 1 is this variable up here. So it's when we assign a random natural to divisor minus 1, it's going to be 0, greater than or equal to 0. We want to ensure that the divisor is not 0. So we add 1 to divisor minus 1, and this gives us the guarantee that regardless of the random natural that's generated for divisor minus 1, if it's 0, divisor will be greater than 0. And so in this expression, we're testing to see that when we add the divisor to the dividend, that the modulus doesn't change. And this is basically like a fundamental property of the modulus operator. It's always going to restrict the range of values that the result assumes. So a let formula, let with the little asterisk next to it, attaches values to names. And the scope of the let opens with a parenthesis, then the keyword let. And the scope continues with a sequence of name-value bindings and ends with a formula for the value to be delivered by the let. And then a final parenthesis closes the scope of the let. Each binding in a let has the form h, v, where h is a name and v is a formula specifying a value to be associated with that name. And also take note of the parenthesis as well. That's an important part of writing each binding. And it's important to note that h does not denote an operator. The parentheses, again, around each binding are required, and any of the names attached to the values in the bindings denote those values at any subsequent point within the scope of the let. But the name-value associations do not extend outside that scope. And scope is a concept that we also encounter in computer languages such as Java, in which we might have local variables in a function that don't exist anywhere else except in the function. And there can be any number of bindings in a let. The most common use of let is to give names to values needed more than one place in a computation. But sometimes let is used to provide mnemonic names to make a formula more easily understood. And the parentheses in a let formula are tricky. We've already kind of looked at that. And each individual binding is enclosed in parentheses, and the whole sequence of bindings is enclosed in yet another set of parentheses. In addition, the entire let formula is enclosed in parentheses. And a let formula delivers a value, which we're calling v subscript let. And this is the value of v sub let is specified by a formula after the name value bindings. So you can see we have our keyword let, we have our name value bindings, then we finally have vlet, which is a formula that we're utilizing to set the value returned by let. And here's another test. We can also test another aspect of modulus. Here we're testing to see if x mod m is less than m when m is greater than 0. So you can see we're defining mod upper limit test. We're also defining a couple variables, divisor minus 1 and dividend. And then we're also adding 1 to divisor minus 1 to create a new variable called divisor. Again, this is going to help us avoid a 0 divisor. You can put comments in to the code that you write in ProofPad. A comment starts with a semicolon and continues to the end of the line. And here you can see the test. We're testing to see if the modulus of, or dividend mod divisor is equal to divisor. This essentially, we're testing to see if the dividend mod the divisor is less than the divisor. This is the test that is specified here at the top of these slides. And so we already have the assurance that m is going to be greater than 0. And m down here, of course, is called divisor. So we want to make sure we don't end up with a 0 as the divisor because that causes overflow. And of course, we don't want that. And the test, again, is just testing to see if if the modulus of dividend and divisor is less than divisor. And if this test passes, in ProofPad, we've essentially shown that this expression is true, and it serves as the basis for writing code that is potentially less likely to fail. And here's an axiom about natural numbers. We're thinking about a function called natp, and we pass in x, and what we're assuming is natp will tell us if x is a natural number. And we're also, part of determining whether a given number is a natural number is first determining if it's an integer. And you can see we're calling this function integer p, which will tell us whether the argument x is an integer. And again, an integer is a little bit wider scope than a natural number because an integer can also be negative. But we're talking about whole numbers, numbers that don't have a fractional component. And we're also testing to make sure that x is greater than or equal to 0. And we're using this and to make sure both of these arguments are true. You should just take note again that integer p of x is true when x is a whole number and false otherwise. So by utilizing this call to integer p, we're basically restricting ourselves to numbers that don't have a fractional component. And here you can see we're checking to see what the result is when we perform the division of natural numbers, specifically the remainder. And in this def property, we're again declaring a couple variables, divisor minus 1 and dividend. And then we're adding 1 again to divisor minus 1 to ensure the divisor is not 0. And we're simply testing to see whether or not the result of modulus is a natural number. And we're also testing to see if the result of modulus is less than the divisor. So we've kind of combined a couple tests into one def property here. And this simplifies things to some extent. We can construct sophisticated equations to test. However, sometimes breaking up a sophisticated test into smaller tests, several smaller tests, is a more advantageous way to approach this kind of development. So there's something to be said about the quotient and the dividend. The quotient is always strictly smaller than the dividend when the divisor is bigger than 1, and the dividend is a non-zero natural number. The following test checks for that property. The random value generator for the divisor makes sure the divisor exceeds 1 by adding 2 to a natural number. Similarly, we make sure the dividend isn't 0 by adding 1. And actually, I strongly encourage you to test this out in ProofPad. You can see we have 2 variables, divisor minus 2 and dividend minus 1, and we're adding 2 to the random natural that's generated for divisor minus 2, and we're assigning the result to divisor. This is the first binding in this let expression, and also this ensures that the divisor is greater than 1. So remember, the minimum random natural that we can generate is 0. If we're adding 2 to that, then we're guaranteed that the value assigned to divisor is greater than 1. And we also want to make sure the dividend doesn't end up 0 either, so we add 1 to it. And then we're simply testing to see if the floor of the dividend by the divisor is less than the dividend. And this test enables us to show that the floor operation, which is essentially using modulus to calculate the next integer towards negative infinity, that the result of the call to floor initially retrieves. So the result of a floor is always going to be a natural number if we're working with natural numbers. So that's one thing to keep in mind about floor. And I think towards the end of chapter 3, there's an interesting segment which describes the way floor works and also describes the way ceiling works, which is a similar operation. And also, checking the result of division. Checking the result of division is a matter of multiplying the quotient by the divisor and adding the remainder. If this fails to reproduce the dividend, something has gone wrong in the division process. So here we have our def property division check test. We have our variables. We're also adding 1 to the randomly generated natural, which ensures that this variable in this binding divisor is assigned a non-zero natural number. And then we're simply testing to see if the divisor multiplied by the quotient plus the remainder of dividend divided by divisor is equal to the dividend. And if the division operator is working the way it should, we would expect that this test would evaluate to true. And if it does, then we have the assurance that the division operator, which we utilize through this call to modulus, is actually functioning the way it should.